Okay, good morning, everybody.
Good morning.
Let's get started. So in the previous class, we looked at the block diagram reduction. Any questions? And what we're going to do today is we're going to look at another method of getting the transfer function, and that is using the signal flow. Now, as we're going to see, the signal flow has a systematic way of producing the transfer function. And therefore, we're going to be introducing the Mason's rule, which is going to help us generate the transfer function from the signal flow. So we're going to be talking about signal flow, and the next topic, after we finish the signal flow, will be the time response of linear time invariant systems. Okay, so in the previous class, we looked at taking a block diagram and generating the signal flow from it, and hopefully the conversion from block diagram to a signal flow is straightforward. And we're going to do examples, and hopefully if there are some tricky points, we will point them out. But basically, in the signal flow, there is the transfer function is written above the branch, and then the signals are labeled along the branch with a node. Is that clear, everybody? Okay. So what we're going to start with is we're going to start with introducing Mason's rule. And then we're going to use this Mason's rule to generate the transfer function of different signal flows. Okay, some definitions. The first definition is the loop gain. And this is the product of branches gain by traversing a path that starts at a node and ends at that same node. Loop gain. So let's look at an example of a signal flow and see what this loop gain is. So if we have an input, and we have G1 here, G2, and we have H1, we have G3, G4, H2, G5, and G6. And we have H3. So this is a signal flow, input and output. What are the loops that exist in this signal flow?
Just that one,
Well, we have this loop, G2. We can go back. If we start here, we go G2, we go back to the same point. And again, is G2 multiplied by H1. Together? So we have a loop here. And again, for that loop is G2 multiplied by H1. What other loops we have?
G4, H2.
Very good. We have a loop here that is G4 multiplied by H2. What other loops we have?
G5 and G6.
G5 and G6 is not a loop because they're both going the same direction. I have to be able to go with the arrows and make a loop. You see here, G2, if I continue following the branch, I make a loop. They're both in the same direction.
Is G4, G5, H3 a loop?
Excellent, yes, it is. So we have G4, G5, and H3.
And then do you also have G4, G6, H3?
Very good. G4, G5, and H3. And also we have G4, G6, and H3. G4, G6, and H3. Is that clear, everybody? So here's a loop, here's another loop, here's a third loop, and here is a fourth loop. Okay, so these are the loop gains of the signal flow. The other definition that we're going to need is the forward path gain. And this is the product of gain traveling a path from the input to the output. So if I travel from the input to the output, if I multiply all the gains as I travel, we call that the forward path gain. So looking at this example, what is the forward path gain? I can travel from here, G1, G2, G3, G4, G5. That's one path. I can travel G1, G2, G3, G4, and then G6. So I have two paths. G1, G2, G3, G4, and G5. And I have another path that is G1, G2, G3, G4, and G6. Okay. Another definition that we're going to need is the non-touching loops, which are the loops that do not have nodes in common. So if I look at the loops that we have here in this example, what are the loops that do not have nodes in common? I'm going to take this loop. What is this loop non-touching with the other loops? We have all the loops, so we can look at them one at a time. So we have the G2. I'm going to keep this on. Okay, we have G2H1. And what is another loop that does not touch G2H1? We can take any of the other ones. We can take the G4H2. Both of these loops are not touching. This loop and this loop are not touching each other. We can take G2H1. And another non-touching loop is G4, G5, and H3. So that's another non-touching loop. We can take G2H1 and then G4, G6, and H3. Both of these are non-touching loops. Is that clear, everybody? So these loops that do not overlap, we call them non-touching. So this loop with these loops. The loops here are all touching. They have path in common. Okay. Another definition that we're going to need is the non-touching loop gain. And this is the product of the non-touching loop gains taking any number of times at a time. So looking at the example, we're going to try to see, we're going to start with 2 and then 3 and 4. 2, we're going to take 2 loops that are not touching at a time. We multiply them, multiply their gains. And then when we're done with all the 2 loops that are not touching, we can look at if there are 3 loops that are not touching, we take the product of their gains. Okay, so in this example, we're going to have G2 H1 multiplied by G4 H2. We have G2 H1 multiplied by G4 G5 H3. We have G2 H1 G4 G6 and H3. Together? So these are the loops. This is the loop gains. So we're going to take them, multiply their gains. Everybody got that? Okay, so in this example, there are no non-touching loops that can be taken 3 at a time. But we'll do an example, we'll show what a 3 at a time look like. Okay. So with that, we can introduce the Mason's rule. And the Mason's rule says the following. To calculate the transfer function g of s between the output and the input, we have to calculate the following. The summation over k of t sub k multiplied by delta sub k divided by delta, where k is the number of forward paths and tk is the kth path, the gain of the kth path, and delta is equal to 1 minus the summation of loop gains plus the summation of non-touching loop gains taken 2 at a time minus the summation of non-touching loop gains taking 3 at a time And then plus non-touching loop gains taken for the time, plus minus, till you consider all the cases. Okay. And delta k is equal to delta minus the summation of the loop gains terms that are in delta that touch the kth path. And what that means, we eliminate from delta all the terms that touch the kth path. Okay. Is that clear? As clear as the drive this morning? Okay, we're going to make it clear. So just pay attention because this can be tricky, but if you understand it, it's straightforward. We're going to do examples to illustrate all these. Okay. So nevertheless, this is the Mason's rule. This is the formula to calculate the transfer function. We just have to calculate each one of these terms in this formula. A summation of the over all the forward paths of the forward path gain multiplied by delta k's divided by delta. So let's see how this works. Let's do examples and illustrate it. So let's say we have a system that looks like this. We have G1, we have G2, we have G3, we have G4, and we have G5. And with G2, we have a path back, negative H1. And with G4, we have a path back with a gain of H2. This is the output, and we have a path this way that is G6. And we have G7. And we have H4. And we have G8. Okay. Okay, so we have this signal flow. We're going to calculate the transfer function between the output and the input. So we're going to use Mason's rule. C over R equal the summation over all the paths Tk multiplied by delta K divided by delta. So the first thing is, what is the value of K?
Number of forward paths.
Yes. The value.
Oh, no. Let me get back.
How many forward paths we have between the input and the output?
Just one.
Just one. See it? Okay. So K is equal to 1 because we only have one forward path. And therefore, we can write this as T1 multiplied by delta 1 divided by delta. Okay. So let's take the forward path, T1. What is T1? The forward path gain. What is the forward path gain? Excellent. So T1 is forward path gain, and it is equal to G1, G2, G3, G4, and G5. So this is our forward path. Okay. What are the loop gains? What are all the loops in this diagram, in this signal flow?
G2H1,
G2H1,
G4H2,
G4H2,
and you have G2, G3, G4, G5, G6,
G2, G3, G4, G5, G6,
G7H4.
G7, G7, G8.
Okay, I see. Oh, that's forward.
And we have G7, G4. Okay. G7, H4. Now, one thing I just want to point out here, usually the convention we have is the forward path, the gain is G. The feedback is H, isn't it? But if you look here, it looks like that's reversed. You see it? And therefore, when you, like if you do the problems like this, just make sure you're following the arrow, not the label. I mean, although the label most of the time is going to be like this. Forward is G, back is H. Here is an exception. Why is this exception?
Because it's technically still going like through the cycle forward.
Okay. Any other ideas? I mean, this could have been come from a system that when you modeled it, it says G7, H4, but the way it fits over all the model, it fits like this. Does that make sense? So, like if you were to look at what this block's coming from, it might make sense. This was, you know, to that model, it made sense. But in the overall model, it just fits like this. But irrespective, the label does not matter. Although most of the time, the forward is going to be G, the feedback is H. Pay attention, make sure the arrows are what guides you. Okay, so we're going to look at non-touching loop gains that are taken two at a time. What are all the loop gains that we can take that are not touching, that we can take two at a time? G2, H1, this is a loop gain. It's not touching G4, H2. And then we have this loop, not touching this loop. And then we have this loop, not touching this loop. See it? The three of them? So we have G2, H1 with G4, H2. We have G2, H1 with G7, H4. And we have G4, H2, G7, H4. Is that clear? Everybody? Three loops. This with this, this with this, this with this. Okay, do we have non-touching loops that we can take 3 at a time?
Yes.
Yes, we do. What is the non-touching loop gain taking 3 at a time? We're going to multiply the gain of all the loops. So we're going to have G2, H1, G4, H2, and G7, H4. Together? So 3 loops, they're all non-touching. We can multiply them together. Okay. So then we're going to go back to our Mason's rule and fill in the formula with all the information that we got here. Okay. So before we do that, we're going to calculate the delta. So we have the room here. We can calculate delta here. What is delta equal to from the definition? We're going to take 1 minus the summation of loop gains plus the non-touching loop gains taken 2 at a time minus the summation of loop gains taken 3 at a time. So therefore, delta is going to equal to 1 minus the summation of loop or the loop gains, which are G2 H1 plus G4 H2 plus G7 H4 plus G2 G3 G4 G5 G6 G7 G8 plus the non-touching loop gains taken 2 at a time. So we're going to add to this non-touching loops taken 2 at a time. So we're going to have G2 H1 G4 H2 plus G2 H1 G7 H4 plus G4 H2 G7 H4. What do we have to add to that? We're going to subtract loop gains taking 3 at a time. So we're going to have minus G2, H1, G4, H2, G7, H4. Together? Is that clear? So this is coming from here. This is coming. Sorry, go ahead.
We subtract when they're taking 3 at a time, not half it. I think I had it wrong.
The 2, we add them. The 3, we subtract.
Yeah, I wrote it down wrong. I was making sure.
Okay. Okay. So therefore, we can come to the Mason's rule. And what else we need to calculate before we do the Mason's rule? Delta K. And since we have only K is equal to 1, we just have to calculate delta 1. So delta 1 is going to equal to, so if I come to this delta that I have here, I'm going to remove from delta all the gains or the loops that are touching my forward path. Make sense? So what I'm going to do, this is my forward path. I'm going to remove this forward path. If I remove this forward path, what is it going to be left? only one loop, which is here. Make sense? So all the terms are going to drop, except for this term is going to survive. So therefore, delta 1 is going to equal to 1 minus G7 multiplied by H4. Again, to calculate the deltas, we remove the forward path, and we just keep the terms that will survive if we were to remove the forward path. Okay, so with that, we can calculate the transfer function. G of S is going to equal to C of S divided by R of S, which is going to equal to T1 delta 1 divided by delta, which is going to equal to G1, G2, G3, G4, G5, multiplied by 1 minus G7, H4, divided by delta. Okay, I'm not going to write it underneath, but this is delta and delta. Is that clear, everybody? Straightforward? Almost. Okay, let's make more examples to make it less clear.
So we would just stop there?
Uh,
That's fine.
what else? You want?
No, I didn't know if we had like simplify or something like that.
Well, you can simplify it, yes,
Oh,
if it can be simplified. But in general, again, all these transfer functions are coming, they are expressed as a function of S. So you can substitute for them and try to simplify it. Ultimately, you want a transfer function. Does that make sense? Yes, I mean, if there is simplification that you can do, by all means do it. Okay, especially if you're doing a homework. Okay, so let's look at more examples and just clarify some things that might be confusing. Okay. So for each one of these examples that we're going to do both. We're going to do the block diagram reduction, and then we're going to do the Masons and compare them. So these will act both as examples for the block diagram reduction and also for Masons, the signal flow. Okay, so if I want to find the transfer function for this system, how do I find the transfer function? How else? How?
With block diagram reduction.
We're going to convert it to one block. Is that what he said? Yeah, but how? Anybody want to read me what the transfer function is going to be? What is the trick here? Yes, feedback. This is a feedback loop. This is a feedback loop. Two feedback loops cascaded together. I can reduce this using the feedback loop formula. I can reduce this feedback formula, and then I can cascade them. Make sense? Again, hopefully with time this becomes these graphs very familiar that you can just do it by inspection. Okay, So what we can if we calculate the transfer function, y over r is going to equal the first feedback loop. What is the gain of it going to be? G1 over 1 plus G1 multiplied by H1 together. Again, we're gonna see this so many times, so hopefully everybody will know it by heart. G1 over 1 plus G1 multiplied by H1. And then we have cascade with the other feedback loop. What is the gain of the second one?
G2 over 1 plus G2H2.
Very good.
Can you multiply those together?
Yeah. So what is the overall transfer function? G2, G1, G1, G2. And then we're going to multiply these together. We're going to get 1 plus G1, H1 plus G2, H2 plus G1, G2, H1, H2. Together? Is that clear? Everybody agrees? Okay, so let's take this block diagram and generate the signal flow for it, and then use the Mason's rule. So we're going to have R. We have G1. What is the gain on the feedback loop? This one. What is the gain? What is it? No, we're just converting this to this signal flow. So this is G1. What is the gain of the feedback loop? H1. But because we have a negative sign, what are we going to make it here? Negative H1. Make sense? Negative H1. Does that make sense, everybody? Notice why this negative sign is, this is going to be subtracted the same as multiplying it by a negative sign. So in the previous example, these H's were all positive. So in here, this feedback was a plus sign. Okay. What do we do? Mason's rule. How many forward paths we have?
1.
1. What is the gain of the forward path?
G1, G2.
G1, G2. How many loops we have? 2 loops. Loop 1 is negative G1, H1, and or the loops are negative G1, H1 and negative G2, H2. Are these loops touching or non-touching?
There's nothing in
Are they-
between the two
Are they
nodes.
touching? 'Cause
They're not
there's
sharing any
one right
terms, so
there.
no.
What is it?
They're not sharing any terms, so no.
They're not. So these are not touching. This loop, I can go through here without traveling through any branch that is common with this one. The same thing with this one. Together? I mean, this is confusing, isn't it? Or is it not? Okay. I was going to say it is confusing. We'll do another example that will make it not confusing. But if it's not confusing, the other example is going to make it confusing. Okay. So here is an example of non-touching loops. And this is how the block diagram looks like if they are not touching. But we'll see when they are touching and how the block diagram would look like. Okay, so these are non-touching. And therefore, we can calculate delta is going to equal to 1 minus G1 H1 minus G2 H2. And then we're going to take loop gains G1 H1 G2 H2. Loop gains, taking non-touching loop gains, taking 2 at a time. Again, we have negative sign, so it will cancel out. So this is negative G1 H1 multiplied by negative G2 H2. Together? There is no more than 2 loops, so there is no other terms left. And then we're going to take delta 1. If I remove the forward path, are there any loops left? No. So delta 1 is just going to equal to 1. Together? And therefore, we can calculate the transfer function using Mason's rule. It's going to be T1 multiplied by delta 1 divided by delta, which is going to equal to T1, which is equal to G1, G2 multiplied by delta 1, which is a 1, divided by delta, which is going to equal to 1 plus G1 H1 plus G2 H2 plus G1 H1 G2 H2. Together? How is this different than the one we got with the block diagram reduction? It's not. Should get the same thing. Okay. Okay. Okay, let's do another example. So we have an R. G1. Okay. So we're going to take a look at this block diagram, and we're going to do the block diagram reduction and the signal flow. How do we do using block diagram reduction?
Is it going to be with 2 cascaded feedback loops?
I mean, we can make them if we want to. What is it we do not like about this?
H1.
H1? You don't like H1? I like H1. Oh yeah, I mean, no, probably we don't like the fact that H1 is coming from here. Is that what you mean?
Yep.
It's not H1's fault, but...
Right.
Okay. So how do we solve this problem? I can shift H1. I can, instead of picking from here, I can pick the signal from here. Isn't it? I can move this, instead of being here, it will be here. Now it's going to get multiplied by G2, so I have to divide by G2. And then if I do that, I'm going to have I'm going to move this pickup line and make it come from here. And I have to divide by G2. Sounds good? What do we do next? We have a feedback loop here, isn't it? I mean, usually we see the feedback underneath, but this is a feedback underneath. I could have plotted this with H2 like this. I can get the equivalent of this, and then I'll have another feedback loop. Is that clear? Everybody? So what we can do, we can take this, I'm going to remove the H2 and G2. What is the equivalent of that going to be?
G2 over 1 plus G2 H2.
Excellent. What do we do next? Now this is a feedback loop. So the transfer function is going to equal to G1, G2 over 1 plus G2 H2 divided by 1 plus H1 over G2 multiplied by G1, G2 divided by 1 plus G2 H2, which we can simplify. The G2 with G2 cancels. This is going to equal to G1, G2 over 1 plus G2 H2 plus G1 multiplied by H1. How else could I have reduced this block diagram? Anybody have other ideas? Anybody?
H1 that way.
H1? H1 this way is not easy. I can't, how am I going to move it this way? This is the error signal, remember?
Right,
So there is not an easy way to move it this way.
right.
Anybody else? How about if we move this H2, move it, instead of being here, we moved it to pick up from here. And then we have G2, we have a feedback loop, and then we have a feedback loop. Make sense? So the point I want to make is that there is not like a single way of reducing the block diagram. There might be many ways of reducing it. Okay, so going back to our block diagram, we're going to do it using Mason's rule. We're going to have R, G1, G2, this is H2, negative H1. Okay. So this is the signal flow equivalent of our block diagram. Now, of course, I could have not put this one here. I could have just put this one here and brought it here.
Would they be touching those then?
Well, they are touching. And to emphasize that, I put this one here. So what I'm saying is, I could have done this and just put it from here. But I should understand that this coming from here really means this. Is that clear? I could have removed this one here, and I could have just done it like this, with negative H1, without the 1. To emphasize that, you know, there is an overlap, I put this one here. And looking at these loops here, I mean, you can see it in the block diagram. This is a loop, and this is a loop. Are they touching? They are touching. This branch is common to both of them. You see it? This one going this way, this one going this way. This branch is coming to both of them. So these are touching. And therefore, these two loops are touching. If I take one loop, the other loop, they're touching. Okay. So using Mason's rule, T1 is equal to G1, G2. We have two loops, L1 equal negative G1, H1. Second loop is negative G2, H2. And therefore, we can calculate delta is going to equal to 1 minus L1 plus L2, which is going to equal to 1 plus G1 H1 plus G2 H2. Delta 1, if I remove the forward path, there is no loops left, equal to 1. And therefore, the transfer function is going to equal T1 delta 1 over delta, which is going to equal to G1 G2 divided by 1 plus G1 H1 G2 H2. Is that clear? And we can see this is the same result that we got from the block diagram reduction. Okay. Any questions? Again, we see how these loops are touching. They have this branch in common.
So can you look at it just like if you removed an entire loop, would the other loop be able to remain?
I mean, if they're touching, if I removed another one of the loops, then the other one will be broken. Okay. Okay, let's do another example. Okay, if we're going to do, if you look at this block diagram, we're going to do block diagram reduction. What can we do?
You try and combine G2 and G.
G1 and G2, yes. These are parallel paths. We can combine them together. What is their equivalent going to be? G1 plus G2. This is H1. And therefore, what is the transfer function going to equal to?
G1 plus G2 over N plus G1 plus G2 times H1.
Very good. Excellent. G1 plus G2 over 1 plus H1 multiplied by G1 plus G2. Okay, can I have you do this using signal flow? You want to try it? And then we'll do it together.
Can we see the original drawing?
The original?
The original, the first one.
Okay. You can talk to the person next to you if you like.
I don't know. I have G1 and G2 together. I don't know where to put H1.
About the example, not about anything else.
Yeah, that's good.
They have. That's my logic. I don't know if that's true.
That's the you're talking about
I think
the one you want, right?
Yeah, I think it was a small little like in which it's just big. I could be wrong. I could
Is H1 being subtracted?
Yeah.
No, I just.
I just didn't know that. I didn't know that.
asked.
Anybody got it?
Oh, we're continuing on, I thought we were just drawing it.
Yeah.
Oh. Oh, my bad, I'm sorry.
I mean, you can calculate the transfer function because you can compare it. We calculated it.
I think it's gonna be G1 plus G2 plus H.
G2.
Parentheses or no parentheses?
Parentheses. I think it's gonna be that.
Where about this from input to output?
Yeah, there's one.
There's two.
But there's two.
Because
You're a G2.
forward.
Okay, I'm gonna plot you the signal flow. So at least if
First step.
you've done that, what is the signal flow looks like? We have an R. G2 and negative H1. And this is just a 1 and a 1.
Yeah.
Anybody got something similar?
Can you simplify that one to the left of G, like into one node, technically?
Excellent. Yes, I could have done this like this. G1 G2 and negative H1. These are the same. However, I mean here it's more clear which loop and whether touching or not, versus here you have to understand that this is coming after and this is coming after. Does that make sense? Okay, so looking at this, straightforward now. What is the T1 equal to? How many forward path we have? 2. We have T1 equal to G1, and we have T2 equal to G2. How many loops we have? 2. Negative G1 multiplied by H1, and the second loop, negative G2 multiplied by H2, by H1, sorry. Are these loops touching or not touching? Touching. And again, you can see it here, you can see it here. This loop, they're all touching with, H1 is coming to both of them. Okay, so therefore, delta is equal to 1 minus L1 plus L2, which is equal to 1 plus G1 H1 plus G2 H1. What is delta 1 equal to? If I remove the forward path, there are no loops left. So delta 1 is equal to 1. What is delta 2 equal to? One. I mean, remember here, because I have 2 forward paths, I'm going to have to calculate K1 and K2.
Should they always be the same? Oh, wait.
No,
these are
they
two
should not be the
paths,
same.
so two different.
No, yeah. I mean, each one is going to have its own delta. Okay, so therefore, the transfer function is going to equal T1 delta 1 plus T2 delta 2 over delta, which is going to equal to G1 plus G2 divided by 1 plus G1 H1 plus G2 H2. Okay. Let's do one final example.
Oh, never mind. The H2 on the second part. So it's supposed to be H1.
Yeah.
So you can take it out and match the other transfer function. There's no H2. Yeah.
For T for the denominator, yeah.
Thanks.
Sorry.
Did you notice it because you compared it, or
Yeah, I
just?
compared it.
Okay, very good. Okay, one more example. So you're going to do the same thing. Actually, usually I make a survey at this point asking students who likes the block diagram reduction more and who likes the signal flow more.
Like block.
You
Signal
don't have to
flow.
transfer from.
Well, then that makes it more.
Okay. The good thing is in the exam you will not have a choice. But you can do it as extra credit and convert it and verify your answer. Okay, you're gonna try to do this with the block diagram reduction and then with signal flow. Can I give it a try? Block diagram reduction. How do you do block diagram reduction?
Would you try and move the top root to the right of G1? By
Yes.
dividing, or multiplying times 1 over G1?
Yes.
Okay.
What else you can do?
Could you move the bottom root?
Yes, we can move this one to before.
Okay.
So, this is so close. This is 205, right?
You're
Yeah.
You're
Oh.
here.
Yeah.
We're in class right now.
Do you mind if I say here?
Yeah,
Go ahead.
Stop.
But you're gonna do the exercise. We're doing this exercise.
What is this?
Linear.
There's a signal flow and block diagram reduction.
Is this like E class?
Yes, it's control class. Okay, so one way we can do it, we said we can do 1 over G2. One over G1. Thank you. Okay, so moving it, this did not get multiplied by G1, so moving it will multiply by G1. Or we could have done G1 H1, and then we're gonna have G1 together, either one of these. What is the transfer function here? 1 over G1 multiplied by H1 multiplied by 1 plus G1. What is the transfer function here? G1 over 1 plus G1 This is H1 multiplied by 1 plus 1 over G1. G1 with G1 is going to cancel. We're going to get 1 plus G1. Okay, so let's do the signal flow. So this is A or B. So if we plot the signal flow, we're going to have G1 this is the output, this is 1, negative H1. Okay. What is the forward path gain? T1 equal to G1. Second path, T2 equal to 1. If you remove either one, we're not going to have any loops. So delta 1 is equal to 1. Delta 2 is equal to 1. How many loops we have? One loop. Negative G1 multiplied by H1, and therefore the transfer function is going to be 1 plus G1 divided by 1 plus G1 multiplied by H1. Is that clear, everybody? Any questions? Okay. Now we have homework this week. It has some block diagram and signal flows exercises. Okay, so in the next class, we're going to start the next topic. Now that we know how to take a complicated system and reduce it, we're going to have, after we reduce the system and get the transfer function, we're going to look at the output of the system. So we're going to look at first order, second order, and higher order system and see how the response of them is going to look like. Sounds good? Okay.